Have you ever looked up at the night sky, at those countless stars, and wondered, why don't we hear from anyone else? Billions of galaxies, each with billions of stars, and likely trillions of planets. Surely, the universe should be overflowing with life, intelligent life, and yet silence. This mystery is often called the Fermi Paradox, and one of the boldest answers to it is the rare Earth hypothesis. The idea that while simple microbes may be common, the evolution of complex, intelligent life like us requires such a delicate and improbable chain of circumstances that Earth might truly be one of a kind. The rare Earth hypothesis was first laid out in the year 2000 by paleontologist Peter Ward and astronomer Donald Brownlee in their book Rare Earth: Why Complex Life is Uncommon in the Universe. For decades before, the dominant view among astronomers had been shaped by thinkers like Carl Sagan and Frank Drake. Their optimism was simple. Planets like ours must be everywhere, and so life, and even intelligence, must be everywhere too. The Drake equation even tried to put numbers on it, often suggesting millions of civilizations in our galaxy alone. Ward and Brownlee took that optimism and turned it upside down. They argued that the Earth's story is not typical at all, that it's the result of an incredibly unlikely combination of astrophysical, geological, and biological coincidences. According to them, the fact that we are here to wonder about our place in cosmos might be far rarer than we ever imagined. Let's start big with the galaxy itself. Earth isn't just lucky to orbit the right star. It's lucky to even exist in the right neighborhood of the Milky Way. Much of our galaxy is hostile to complex life. Near the galactic center, stars are densely packed, and supernovae or bursts of radiation from the supermassive black hole could sterilize entire regions. Go too far out toward the galactic fringes, and you find stars that formed with too few heavy elements, what astronomers call metals. Without those elements, no rocky planets, no chemistry for life. So complex life requires a sweet spot, the so-called galactic habitable zone, a narrow ring, perhaps only about 10% of stars in the Milky Way, where conditions are stable enough and metal-rich enough for life to even have a chance. But that's just the beginning. A star also needs a stable orbit around the galaxy, avoiding spiral arms crowded with stars where the risk of cataclysmic events is higher. The Sun's nearly circular galactic orbit, sitting in a quiet suburb of the Milky Way, might be yet another piece of extraordinary luck. Not every star is suited to host life as we know it. Our Sun, it turns out, is usually well behaved. It belongs to a rare group of stars stable enough to sustain liquid water on nearby planets for billions of years. First, there's the habitable zone, the Goldilocks region, where water can exist as a liquid. But staying in that region isn't enough. Stars gradually brighten as they age, meaning the habitable zone shifts outward. For complex life, a planet must remain in this zone for hundreds of millions, sometimes billions of years. That continuously habitable zone is astonishingly narrow. For a star like the Sun, roughly between 0.95 and 1.15 astronomical units. The Sun is also stable. Its luminosity varies by only about 0.1%, far less than many stars. A star with wild fluctuations could easily freeze or boil away oceans. And it matters that Sun is solitary. Over half of stars are binaries, where gravitational disruptions could destabilize the planetary orbit. Stellar type matters too. Massive stars like Sirius or Vega have broad habitable zones, but they burn too hot and fast, flooding planets with sterilizing ultraviolet radiation long before life could evolve. On the other hand, red dwarfs are long-lived but problematic. Their habitable zones are so close that planets tend to be tidally locked, with one side scorched and the other frozen, not to mention frequent solar flares. That leaves only a narrow band of stellar types, F7 to K1, with G-type stars like our Sun right in the sweet spot. Yet these are rare, only about 9% of stars in the Milky Way, and not just any G-type stars will do. Metallicity matters. Heavy elements forged in ancient supernovae are essential for building rocky planets and complex chemistry. Stars poor in metals like those in the early universe or in globular clusters are unlikely to host life-bearing worlds. All of this makes our Sun extraordinary, stable, metal-rich, solitary, and middle-aged, providing just the right conditions for just the right amount of time to nurture life. Now we arrive at the planet itself. The idea of the habitable zone is familiar, the region around the star where liquid water can exist on the surface, but it's a razor-thin balance. If Earth's orbit were just 5% closer to the Sun, we'd be more like Venus, scorched and lifeless. If it were 15% farther, we'd resemble Mars, frozen and barren. And it's not just distance. A habitable world must have had the right size. Too small, like Mars, and it can't hold on to an atmosphere or sustain plate tectonics. Too large, and it risks becoming a gas-shrouded mini-Neptune with crushing conditions hostile to land-dwelling life. Earth once again sits right in the middle, big enough to hold oceans, small enough to keep continents above water. But what really makes Earth exceptional is not just its orbit or its size. It's a set of rare interconnected features that worked together to make our world uniquely stable and hospitable. Four stand out: plate tectonics, the magnetic field, our moon, and Jupiter. Plate tectonics. Earth is the only known planet with active plate tectonics, the slow movement of huge slabs of crust across the surface. This constant recycling of crust drives mountain building, volcanoes, and earthquakes, but it's also essential for long-term habitability. By subducting carbon-rich rocks into the mantle and releasing carbon dioxide back into the atmosphere, tectonics acts like Earth's thermostat, regulating the greenhouse effect and keeping temperatures stable for billions of years. Without it, Earth might have ended up like Venus with a runaway greenhouse, or like Mars, frozen and barren. Tectonics also creates a dynamic landscape, continents, shallow seas, and varied ecosystems, fueling biological diversity. A protective magnetic field. Deep within Earth, the churning of molten iron in its outer core generates a powerful magnetic field. This invisible shield deflects the solar wind that would otherwise erode our atmosphere and bathe the surface in radiation. Mars is the cautionary tale here. Once, it may have had rivers, lakes, even oceans, but without a global magnetic field, its atmosphere was stripped away, leaving it dry, cold, and hostile. Earth's magnetosphere doesn't just protect the air we breathe. It protects the stability of our climate and the very possibility of long-term habitability. A giant moon. Earth's moon is extraordinary. Relative to its planet, it's the largest in the solar system, about 1.2% of Earth's mass. The size matters. The moon stabilizes Earth's axial tilt, keeping it within a narrow range of about 22 to 24 degrees. Without this anchor, Earth's tilt could wobble chaotically over millions of years, producing extreme swings in climate, ice ages followed by blistering heat that might have made complex life nearly impossible. The moon also drives tides, which early in Earth's history were far stronger. Those rhythmic rises and falls of oceans may have created the tidal pools where life first experimented with complexity, bringing the gap between sea and land, and its very origin, the result of a colossal impact between the young Earth and a Mars-sized body, is another extraordinary accident that may have been essential for our story. Jupiter, the cosmic shield. Out in the outer solar system, Jupiter plays an unsung role as Earth's protector. With a mass more than 300 times that of Earth, Jupiter's gravity dominates the solar system, flinging many incoming comets and asteroids into harmless orbit or absorbing them outright. Astronomers estimate that without Jupiter, Earth would face catastrophic impacts far more often. Life may still have emerged, but it's doubtful complex organisms could have flourished amid constant bombardment. And it's not just Earth. Jupiter's gravitational dance has shaped the entire architecture of our solar system, preventing another giant planet from forming in the asteroid belt and allowing a stable Earth to exist in the first place. Put together, these four features aren't just helpful extras, they act like guardians, protecting and balancing Earth in ways that let life thrive. Without even one of them, our planet might never have moved beyond microbes, and perhaps life as we know it wouldn't exist at all. Even with all these conditions, life's road to complexity was anything but straightforward. For the first 2 billion years, Earth hosted only simple microbes. The leap to complex cells, eukaryotes with nuclei and organelles, was a staggering evolutionary bottleneck. On Earth, it happened once and only once, suggesting it might be vanishingly rare elsewhere. Then came the great oxidation event when photosynthetic microbes filled the atmosphere with oxygen. An environmental catastrophe for early life, but ultimately essential for complex organisms like us. Earth also endured snowball Earth episodes, global glaciation that nearly wiped out life but may have spurred evolutionary innovation. And then, around 540 million years ago, the Cambrian explosion unleashed an extraordinary burst of multicellular diversity. Was that inevitable or another improbable stroke of luck? Even after complexity arose, mass extinctions shaped the path of evolution. The asteroid that ended the age of dinosaurs cleared the way for mammals and eventually humans. But had extinction events been too frequent or too mild, the story of Earth might have ended very differently. So, what's the answer to the Fermi Paradox? Where is everybody? Well, the rare Earth idea has a simple answer. Maybe they're not there. The universe isn't strangely silent, it's just mostly empty. Think of it like this. There might be other intelligent species out there, but they are so incredibly rare and spread out that the closest one could be billions of light years away. That's an unimaginable distance, making it impossible for us to ever hear them or talk to them. In this view, simple microbial life might be common across the galaxy, but the jump to complex, intelligent life that can build technology, that might be a miracle so rare that it might have only ever happened once, right here. Of course, the rare Earth hypothesis hasn't gone unchallenged. Scientists and thinkers from multiple disciplines have raised important criticisms that deserve attention. Accusations of anthropocentrism. Some critics argue that the hypothesis is overly Earth-centric, assuming complex life must follow Earth's blueprint. Biologists like Jack Cohen call it restrictive and even circular reasoning. Writer David Darling suggests it's not predictive but merely describes Earth's history as if it's universal. Others warn that the hypothesis is sometimes co-opted by intelligent design proponents, though Ward and Brownlee themselves attribute Earth's uniqueness to chance. More exoplanets than it anticipated. When the hypothesis came out in 2000, exoplanets were rare. Now thousands have been discovered. Many Earth-sized rocky worlds orbit within habitable zones, especially around common red dwarf stars. While Ward and Brownlee excluded these stars, exobiologists point out they may still host life under the right conditions. Rocky planets in habitable zones might not be rare. Analysis of Kepler data indicate that around 20% of G and K-type stars may host Earth-sized planets in habitable orbit, potentially billions across the Milky Way. Alternative models suggest rare Earth estimations of habitable planets could be overly pessimistic. Jupiter may not be a perfect shield. The idea that Jupiter protects Earth isn't universally accepted. Some simulations suggest Jupiter might even increase Earth's impact risk in certain contexts. In fact, objects like Maxwell's Comet, one of the closest near-Earth passes known, were nudged by Jupiter's gravity. Red dwarf systems might defy assumptions. Though Ward and Brownlee argue red dwarf habitable zones are too hazardous due to tidal locking and flares, critics point to worlds like Proxima b and the TRAPPIST-1 system as rebuttals. This suggests that life in such systems may be more plausible than the rare Earth allows. Evidence of tectonics beyond Earth. Ward and Brownlee dismissed tectonic activity elsewhere, but recent missions have revealed tectonic-like features on ice bodies like Pluto and Charon, challenging the uniqueness of Earth's plate tectonics. The pushback against the mediocrity principle. Philosophers point out that the rare Earth idea clashes with the long-standing view that Earth is nothing special. If our planet really is that rare, it leaves us with a puzzle. Why do we exist here to notice it? This puzzle is often called anthropic bias. Is the hypothesis testable? Many rare Earth parameters like plate tectonics or presence of large moons are currently undetectable around exoplanets due to technological limitations. This makes the hypothesis hard to confirm or falsify with current data. It may simply describe Earth's past. Some researchers argue that the rare Earth hypothesis doesn't propose a universal mechanism. It simply recounts Earth's specific narrative. This is more descriptive than predictive. The rare Earth hypothesis doesn't claim Earth is the only cradle of complexity, but it does suggest planets like ours may be unimaginably rare cosmic oases separated by vast oceans of sterile space. If that's true, then we're not just residents of an ordinary world in an ordinary galaxy. We may be the beneficiaries of a cosmic jackpot, one that makes Earth not just a home but a treasure beyond measure. And in that light, the silence of the stars becomes less a mystery and more a reminder of how rare, how fragile, and how precious life on Earth truly is. Thanks for watching. If you found this video helpful, give it a thumbs up and don't forget to subscribe to the channel.